In Chapter 9, we're going to be focusing on alcohols and some of the chemical reactions that are related to those. And some of the related compounds, ethers, epoxides as well, we'll cover in some amount of detail. The focus here is really going to be on alcohols, so the functional group OH, ethers where it's an oxygen in between two sets of carbon groups, and epoxides that form this kind of triangle here between two carbon groups, and these are going to have special chemistries that are involved in each of these. Now, we're not going to be talking about enols or phenols. These sets of elements undergo different chemical reactions, mostly because of the double bonds nearby the lone pairs in the oxygen. So these will have special different chemistries associated with them because of that sp2 hybridized carbon and the closeness of these lone pairs to these pi orbitals. Naming here should be a review from previous classes, but we add the OL ending hexanol for the functional group alcohols, and it's the same longest chain, and then add the OL ending, and we'll need to determine which carbon that is on based off of allowing for the shortest, the smallest numbers on that primary, that higher order substituent. So an example here is a chain that's 1, 2, 3, 4, 5, 6 length long, so it's going to be a hexane, but we're going to number it so that the OH group gets the lowest number. So it's there's a 5-methyl hexane 3-ol. Here we're using that numbering system where you put that 3 next to the functional group ending. A couple other examples here with cyclic compounds. We're always going to number on the priority group. The alcohol is a priority over a methyl group. So we have the 3-methyl cyclohexanol. We don't need the 1 because it's inferred that we're going to be starting the numbering on the higher priority alcohol group. Here we do this so that we have the lowest numbers on all of the groups. So 1, 2, we count from the right side counterclockwise to the pair of methyl. So 2, 2, 5 trimethyl cyclohexanol. It's a couple examples of naming cyclic compounds with alcohols on them. A lot of simple alcohols will have some common names. Ethylene glycol, for example, the IUPAC name would be ethane 1,2-diol, but it's typically called ethylene glycol. Glycerol is another very common, the glycerol backbone on triglycerides or fats. This is what's kind of cleaved off from the fatty acid and left over. This is common in some of that, if you've seen people using vape pens or smoke machines, this is typically what is used in there to give that kind of smoky appearance when the smoke machine goes off. It's typically a glycerol water solution that gives you that type of vapor. And here's an example of that we can have differences, obviously, on our cyclic structures, the cis or the trans. Need to make sure that we're keeping track of that on cyclic compounds. So just some more naming that should be review. Other groups that are a little different, but you've heard of isopropyl alcohol because we have that alcohol off the middle, another just a common name, not an IUPAC name, but this can also be used as a substituent group off of a longer chain. Sometimes you'll have an isopropyl alcohol group as well. So pause here, do some quick practice on the naming, make sure you've got this down, and we can cover this in class if you have questions about it. Simple ethers, for naming these, a lot of them will have assigned common names. And for example, we have a sec-butyl methyl ether. So we put one substituent group and then the other substituent group and just ether as the base word. So sec-butyl and then a methyl ether, diethyl ether. So you have two ethyls on either side. So you can have the symmetrical or asymmetrical version of that. Here's a tetrahydrofuran, which is a very common aprotic solvent. A lot of ethers can tend to be good aprotic solvents because they have some polarity to them because of the oxygen, but they are not attached to hydrogen bonds, so they can't hydrogen bond and therefore are aprotic. Otherwise, we also have some substituent groups. If you have it on a longer chain, these can be also described as just substituent groups as methoxy, ethoxy, the OXY ending, it gets added on as telling you how many carbons are past that group. Here's a tert-butoxy, just a few different examples, right? You might have sec-butoxy. So depending on that chain, if it's not too long, you'll sometimes see that as part of that name as well. If we were going to give this compound an IUPAC name, the first step would be to find the longest chain. So we have 1, 2, 3, 4, 5, 6, 7, 8 is actually the longest continuous chain here of carbon. And then we have this substituent group, which is an ether. So we have a methyl ethyl, an ethoxy group. So we write that the base name is 8 for the octane, and then the 1, 2, 3, 4 carbon, it's going to be a 4 ethoxy octane. All right, so take a few seconds to name these groups, and then we will go over the answers. The first group is methyl ethyl propyl butane. So we have a butane. So we'll have a 1-methoxy butane. For B, we have a cyclohexane. And since there's only one substituent group, we would just say it's a methoxy group, methoxy cyclobutane. For C, let's find the longest chain, 1, 2, 3, 4, 5, 6, versus 1, 2, 3, 4, 5, 6, 7. So this is the longest chain. It's going to be a hexane, and we're going to number it from this carbon because we hit some of the substituent groups first and the higher order methoxy group. So it'd be the 2-methoxy, 3-methyl, 4-ethyl heptane. Since the 4 is alphabetically first, that one in front. This third group has 2 substituent groups off of the chain, and you'll notice that they are at different angles. So we'll have they're trans from each other on either side, and we'll number with the higher order group 2, 3, and 4. So we have the base is a cyclohexane, and the substituent groups are 4-ethyl, 1-propoxy, and this will be a trans conformer. Epoxides have special chemistries associated with them because of this strained 60-degree bond angle. If we go back to some of our understanding of how the energy involves, you can kind of think of this as high energy, which means it also has high potential energy. So high potential to interact with other things and allow this to break to relieve the stress of that ring. So these are called epoxides or oxyrings. Those are 2 different words for that. You can see the difference between alcohol, the condensed nature of that negative charge in alcohol versus the ether versus the epoxide. So you can see this is a darker red, deeper red, and it is enriched in there, which provides a high energy potential for epoxides. When naming epoxides, we always number the rings. We always give the groups under that epoxide, that bonded oxygen, that kind of triangular oxygen, we always number those consecutively. So we never would go around the ring and end at that higher number of 6 here. It's always 1, 2. The direction of that would obviously depend on allowing us to provide the different the groups off of that, ideally with lower numbers, if that makes sense, but we also have to find the longest chain as well. So in this instance, you might think, oh, let's start here, then we have two substituent groups, but we actually want this chain, this is a priority group, so you want to have this as the lowest number. So 1, 2, and 3, so that we get the propane. And on the 2, we get a methyl, and we have a 1, 2 epoxy. So we provide both of the numbers where the oxygen is bonded. We provide both of those. You can see the 1, 2 there. Here's an example of where that's going to come off. So we can have, just like any other ring, we can have cis versus trans versions depending on which side of that ring those groups are coming off. We have 1, 2, 3, 4, 5. So we have the pentane. That epoxide is between the 2 and the 3 carbons here. If they're named as this other functional group, or just the same functional group, just different naming techniques and styles, it can be considered an oxyrane. So you start numbering at the oxygen and go around that ring, and so this would be considered a 2,2-dimethyl oxyrane. So just different ways to name them. We'll typically use the epoxide because this gets kind of cumbersome depending on what the substituent groups are off of that ring. Here's some practice naming these rings. These more simple compounds, you can name them as both the epoxide and the oxyrane. This one, now that we get more complicated, you can't do that as easily. So just an example of that. So if you have questions about naming these or what these should be named, we can cover that in class. The differences in the properties between these three different kinds of functional groups are pretty obvious when we think about intermolecular forces, and here obviously the oxygen is attached to a hydrogen, so we can have hydrogen bonding. And now that we know a little bit more about hydrogen bonding, we could also look at the ability for that oxygen to hydrogen bond based on the classification. So if we have a primary hydrogen or a hydroxide or a primary alcohol, we have more of an ability to hydrogen bond because this is free and more able to rotate around and interact with other things and be less sterically hindered. As we move over to a secondary and tertiary alcohol, this group becomes more sterically hindered and is less able to hydrogen bond. So primary alcohols will have lower lower steric hindrance, but higher ability to hydrogen bond and generally higher boiling points and melting points. And when we get to tertiary, that will then reduce the effectiveness of the hydrogen bond, and those boiling points and melting points will change with the change in intermolecular forces. Here is a summary of that and just describing what I just mentioned on the last slide. Just as an example, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, right? These all have 4 carbon groups in them, but we have with primary alcohol, we would get 118 degrees as the boiling point. Because we have this more substituted group alcohol now, the secondary, we have more steric hindrance. That drops to 98. So that is about 20-degree difference in jump. We go to a tertiary and we lose another 15-ish degrees. So there's a reduction in the ability for that to hydrogen bond here. Part of it's how this can lay down on itself. The other part is some of the steric hindrance for the alcohol. And then we can see that with this non-hydrogen bonded group here with the ether, we cannot do any hydrogen bonding. So then we drop a lot more from even a tertiary alcohol when we go to ethers. And along with the boiling point changes depending on the type of functional group, we also, the general rule of thumb is approximately every 5 carbons there should be a water-soluble functional group on there, and that will give you an idea if it might be soluble or not. Based off of that information, we should pretty quickly be able to rank these compounds, and this is something that I would like you to do. I won't go over the answers with you now, but if you have questions about this, I'd be happy to discuss this in class. Some common uses for alcohols, methanol is also called wood alcohol because it's typically generated from heating up wood at high temperatures. We can also get this as a byproduct in fermentation when we're generating ethanol for various purposes. And also here is the propane 2-ol or isopropanol, otherwise known as rubbing alcohol, is a common name. It is able to sterilize many different instrumentation. It's really good at 70% for sterilizing surfaces. It's commonly used. Ethylene glycol is another common alcohol. It's a lot of times used in antifreeze. A lot of ethanol is actually created from corn. That's a lot of our crops, our corn crops are actually not sweet corn that you would eat, but it's actually utilized to generate ethanol for what's called gasohol or E85. So it's a mixture of long chain carbons with the addition of ethanol that helps to reduce some of our CO2 in the atmosphere by some of the take up of those plants to pull out some of the carbon dioxide that's actually generated from fossil fuels, which are non-renewable sources of fuel. So from some interesting common alcohols that are used to ethers, one of the more common general anesthetics from the 19th century is diethyl ether, this first compound on the list here. It was readily available and easy to generate, but it's also highly flammable and can make the patient pretty nauseous. So at the time, it was great because there were fewer alternatives to surgery, anesthetic for surgery, and this was very commonly used. Now, the more common is used sevoflurane, which is this compound in the middle. A lot of fluorinated groups off of this ether, and it does also provide general anesthetic, but it's non-flammable, and it also reduces quite a bit some of the patient discomfort. So it's replaced this diethyl ether that makes people nauseous and feel more sick. This doesn't have those side effects. Now, the other thing that's interesting, there is called this crown, these 18 crown 6s, basically telling you how many carbons versus how many oxygens are involved in these crowns. And these are ether crowns. They're pretty interesting because they create this host-guest complex where the host is the crown ether and the guest is an ion. And these can be really effective. You'll notice that they like to interact with positive. So this is a potassium, this is a lithium ion. Notice that they're positively charged groups that get associated. What does that mean? Well, it means that usually if there's a positively charged ion in solution, there's a negatively charged ion in solution. That means that we can use these crown host-guest complexes to isolate positive charge and allow for a really great negatively charged nucleophile or base to be floating around in our solution to undergo substitution or elimination reactions. Here is just an example showing that potassium cyanide, for example, if we have a different type of 18 crown 6 compound that's shown here, we can solubilize that potassium ion, and then we allow that negatively charged nucleophile to then undergo this rapid, strong nucleophilic substitution reaction. So these crown ethers can be very helpful in helping to generate a stronger nucleophile. So this question on the bottom, you should be able to answer based off of what the type of nucleophile is. Epoxides are found in biological systems fairly often, sometimes anyway, not a ton, but we can find them in different biological systems. In fact, some of these different gypsy moth, green stink bug, and cockroaches all have these epoxides within some of their sex hormones that they use to attract other insects. And these are different epoxides that have been synthesized for various reasons. The eplerenone is also the trade name Inspira. It's used to reduce cardiovascular risk in patients that have already had heart attacks. So this is actually a mineral corticoid receptor antagonist. It helps to block aldosterone, which raises blood pressure. On the right here is another epoxide that is a bronchodilator that helps patients with COPD or chronic obstructive pulmonary disease. You may have heard of this recently in terms of the coronavirus that affects people that have this issue more generally than the general population. Generating ethers, we have looked at how to do this in the past. Alcohols and ethers, we can utilize typical substitution reactions where we generate strong nucleophiles that then can attack the halogenated compounds to generate, for example, an alcohol if we're using hydroxide as our nucleophile, or if we have a methyl group attached to our oxygen, we can generate the ethers. This bottom has a specific inventor of this. It's called the Williamson ether synthesis, but we can just refer to it as a typical SN2 reaction. If we have these type of reactions, with ethers, we can do this process in two different ways, right? We can, for example, for something that it looks like this, ethyl isopropyl ether, where we have an isopropyl group or an ethyl group. The first way we could generate methyl ethyl, right? We could have an ethyl group on our negatively charged oxygen that is going to attack this secondary bromide. So that would be one option. Or the other option is that we would have our halogen on this straight chain ring, and we would have our nucleophile be this with the isopropyl group. So two different possibilities. What would be the best pathway, do you think, for generating the same compound? The best pathway is going to be the one in which this SN2 reaction is going to happen more quickly. If in this pattern, right, we're going from this oxygen lone pair of electrons, we're attacking this carbon here, and it's a secondary carbon. So that means that we're going to have more steric hindrance here than we are going to be in this direction where this is a primary carbon. So this pathway B is actually the preferred pathway because it's going to happen more quickly, and pathway B, that SN2 reaction is less sterically hindered. One really great way to generate the alkoxide nucleophile is by using sodium hydride. So sodium hydride is going to allow the hydrogen to be negatively charged, and that will help to be a very strong base for pulling off this hydrogen from the oxygen. And so then we generate this alkoxide nucleophile. And the H2 is also nice because this is going to have a really low boiling point. It'll bubble, gas will form as it attaches as we create this H2. And you can just bubble this out of the solution. And then you can help drive that reaction towards the products, because we are removing some of that product. For forming epoxides, we generally want to have an alcohol group, and on an adjacent carbon, we're going to have a halogen. And what happens then, for example, if we use sodium azide again, or some other strong base that can pull that hydrogen off of that alcohol group, that will form this alkoxide. And this is just a typical SN2 reaction. It's just happening within the same molecule. So the lone pair of electrons here will attack this partially positive carbon and bump off that halogen. And then we have generated our epoxide. So far, we have spoken about how we can generate some of these functional groups from other reactions that we've talked about in the past. We've generated some of these in previous chapters. But now what happens when we have alcohol and we want to do a reaction with that alcohol or change that alcohol into something else? Now, this is where the problem starts because alcohol is not really a good leaving group, right? So that last example, when we're generating that epoxide, we can have a strong nucleophile come in and bump off that halogen. And generally, halogens are pretty good leaving groups. But when we're talking about doing a nucleophilic substitution, for example, and alcohol is that group we're trying to substitute off, now this OH group is a poor leaving group. It doesn't really want to leave that well. So we have to think about different mechanisms that we can utilize to help push off that hydroxy group. And we have to essentially activate or convert that alcohol group into something else to make it a better leaving group. So that's what we're going to talk about in these over the next few slides. One way to allow this chemical reaction to occur or to proceed is to make that alcohol group a better leaving group. And so one way to do that is by using a very strong acid. And so this is generally will be an inorganic acid or something that's a strong acid. We're not going to use a weak acid because we have to have something that's going to have a pKa of generally less than -2. To have this OH group come off, alcohols have a pKa between 10 to 16. So we have to have something strong enough to make this chemical reaction move forward. So if we use a strong acid like hydrochloric acid or sulfuric acid, we'll see these are allowed to then generate this new this OH2 positive. So this will be, the leaving group will be water, which is then actually a really good leaving group. So we're going to talk about transforming these alcohols into other groups so that we can undergo not only substitution reactions with these, but also elimination reactions. And in these elimination reactions where we are pulling off oxygen and hydroxide, which then forms H2O or water, we call these dehydration reactions. So the next few slides are going to cover these dehydration reactions and how to get these substitution reactions with a poor leaving group initially of alcohol. So different strategies for that. So this is as far as I'm going to go here. This is a good stopping point because then we get into a lot of different chemicals and maybe perhaps new chemicals and compounds. I think this is a good place to stop, and we'll cover any of the questions you have of the problems that we've covered up to this point, and then continue on in our next class period.